Hello learners, ready for some math magic? Let me start with a puzzle. Suppose you deposit 100 rupees in a bank and every year the amount doubles. After the first year, 200. After the second year, 400. After the third year, 800. Do you notice something? This isn't just money growing, it's mathematics in action. Such patterns form what we call a geometric progression or GP. A sequence is called a GP if each term is obtained by multiplying the previous one by a constant number called the common ratio. For example, 2, 4, 8, 16. Here each term is twice the previous, so ratio equals 2. Another 1 by 9, 1 by 27, 1 by 81. Here ratio equals 1 by 3. So GP is all about multiplication, while arithmetic progression was about addition. That's the big difference. Let's build the nth term formula step by step. Start with the first term, call it A. The second term is a times r, written as AR. The third term is a times r squared, written as AR square. The fourth term is a times r cubed, and so on. So in general, the nth term is given by a sub n equals a into r raised to the power n minus 1. Example, take a equals 5 and r equals 5. The 10th term is a sub 10 equals 5 into 5 raised to the power 9, which equals 5 raised to the power 10. This formula means no matter how far out in the sequence you want to go, you can jump directly there without listing all earlier terms. Pretty efficient, right? Now, let's look at the types of GP. If your progression stops after a certain number of terms, like a AR square up to AR to the power n minus 1, it's a finite GP. If it goes on forever, like a AR square, endlessly, that's an infinite GP. But here's the catch. Infinite G.P.s only makes sense when the common ratio is between minus 1 and plus 1 in magnitude. If the ratio is larger, the terms explode. If the ratio is smaller than minus 1, they swing wildly. So finite G.P.s are straightforward, while infinite ones lead us into convergence, a deeper mathematical idea. Okay, time to tackle the big question. How do we add terms of a GP? The sum of the first n terms is written as S sub n equals a plus AR square plus plus AR to the power n minus 1. If R equals 1, the terms are all equal to A, so S sub n equals n times A. If R is not equal to 1, we do a clever trick. Multiply the sum by R. Rs sub n equals AR square plus plus AR to the power n. Subtract this from the original sum and almost everything cancels out. We get bracket 1 minus R bracket times S sub n equals a minus AR to the power n. So the formula becomes S sub n equals a into bracket 1 minus R to the power n close divided by 1 minus R. That's the magic formula for summing n terms of a GP. Now, imagine adding an infinite number of terms. Sounds impossible, right? But sometimes it works beautifully. The infinite sum is defined as the limit of S sub n as n tends to infinity. If the absolute value of R is less than 1, then R to the power n approaches 0 as n grows. In that case, the formula becomes S equals a divided by 1 minus R. Example, 1 plus 1 half plus 1 fourth plus 1/8 plus forever equals 2. Amazing, right? An infinite number of terms adds up to a finite value. But if the ratio's magnitude is 1 or more, the series diverges, meaning no finite sum. So, infinite GP works only when the ratio is tame, not wide. Let's flex our problem-solving muscles with a worked example. We have the GP, 2, 8, 32, and so on. Which term equals 1,31,072? Step 1. Identify. First term equals 2, ratio R equals 4. Formula. A sub n equals AR to the power n minus 1. Step 2. Substitute. 1,31,072 equals 2 times 4 raised to the power n minus 1. Simplify. 65,536 equals 4 raised to the power n minus 1. Step 3. Recognize that 4 raised to the power 8 equals 65,536. So n minus 1 equals 8. Therefore, n equals 9. So, the ninth term of this GP is 1,31,072. Notice how the formula saves us from listing all terms one by one. Let's talk about the geometric mean, a very useful cousin of the GP. The geometric mean of two positive numbers a and b is square root of ab. For example, between 2 and 8, the geometric mean is 4. So the sequence 2, 4, 8 is in perfect geometric progression. We can even insert more numbers between a and b to create a GP. For instance, between 1 and 256, inserting 3 numbers gives 1, 4, 16, 64, and 256. This idea is used in real life too, like dividing investments or splitting growth rates smoothly over time. Time to wrap it up. A geometric progression is a sequence where each term is obtained by multiplying the previous by a constant ratio r. The nth term is given by a sub n equals ar to the power n minus 1. The sum of n terms is a into bracket 1 minus r to the power n close divided by 1 minus r for r not equal to 1. For infinite series where absolute value of r is less than 1, the sum is divided by 1 minus r. We also saw how to find specific terms, sum up series, and use geometric means to insert numbers in between. And that, dear learners, is the power of GP. It explains compound interest, population growth, depreciation, and even how bacteria multiply. In the next video, we'll explore the relationship between arithmetic mean and geometric mean, a fascinating link between addition and multiplication. Stay tuned and keep progressing geometrically.